Right, class, thank you for joining me once again. Do sit down, stop throwing those paper darts, cross your arms, fold your legs, other way around if you like. Pay attention. This is very important. One of my supporters on my fine channel has suggested to me, well, not so much suggested as asked question of me that I thought, well, I might as well answer it because why not? I didn't see any other good answers to this particular question available on the interwebs so much, at least not that spoke very well to me. So I thought I'll make this one. Why not? Obviously, we're talking about how it is that we know absolutely that the distance between the Earth and the Sun is roughly 93 million miles. So to answer that question, thank you, Risa, for the question. It's really quite simple. Logically, it's not that difficult to put together. I think you will have to pay a little bit of attention, but that's fine. That's life. I'm afraid. I do need to give you just a little bit of background so that we can understand what it is that we'll be doing here before I get into doing one or two sums for you at the end so that you can see pretty much exactly how these calculations are made and how they are indeed cross-checked to objective reality, that thing that we live in, most of us anyway, the universe over here that we can determine to be objectively real. What are we looking at up here? What is this? Goodness, what's that got to do with anything? Well, I'll tell you what it is. I've gone blind looking at that thing. Take note, Spheriae, don't look at that thing directly without filtration. You'll go blind. That's a picture of the sun taken through a filter to take most of the glare of the sun away so you can actually see what's going on there. This is a photo taken of our sun from the Earth on the 6th of July 2020 at 0100 hours, give or take a few seconds. And what you see in the top left-hand sort of quadrant of the apparent disk of the sun as we look at it is a black dot there. That's Venus. It's Venus crossing between the orbit of the Earth and where the sun is. And so it casts a shadow that we can see. There it is, that little black dot there. Venus, goddess of love that you are, and all that kind of stuff. Venus. Sorry, let's get on with the actual science lesson, shall we, class? Okay, so what has Venus crossing in front of the sun got to do in any way, shape or form with how far away the sun is from the Earth, and how does Venus crossing the sun prove a damn thing? What's wrong with me? Why would I say such ridiculous nonsense? Well, let me explain the ridiculous nonsense to you, those of you who still reside in Flattaria. Here it is, pretty much. Right. History. We need to go back a goodly number of hundreds of years, really, and we need to consider the work of a really quite wealthy astronomer of the time. He was able to afford the best equipment, the most accurate measuring equipment. He was very much interested in astronomy, and he was always making very, very accurate observations of the exact positions of the planets, apparently, in the sky at different times of the year, at set times of the night, and basically, yes, had a great deal of data, which he was keeping on the movements of the planets, the apparent movements of the planets, because obviously movement is only ever relative to an observer. And so apparent movement of the planets in the night sky throughout the year. Lots and lots of data. Very, very good. So there you go. said very wealthy and quite famous astronomer was named Tycho Brahe. Tycho Brahe was his name. And he, near the end of his life, near enough anyway, decided to take on an assistant and to pass on his knowledge such that it was, or some of it anyway, as it turns out, to said assistant that he was taking on, who was a young 27-year-old man called Kepler. You've probably heard of him too. Kepler duly became said assistant to Brahe, only Brahe did not provide Kepler with his data because Brahe was an advocate for the Earth-centric model of the solar system. And he absolutely knew, actually, that his data that he'd collected over many years debunked his own belief structure that he had held and put forth throughout his life prior to that point. And he didn't want it getting out. He didn't want he didn't want Kepler to look at his data because that would have disproved him. So Kepler had to wait, unfortunately, until Brahe died to get hold of his data, which he duly did on Brahe's death. He analysed it as you would expect him to do, and he said, goodness me, there are a number of things that we can pull out of this data. And Kepler went ahead and pulled several things out of that data. In fact, he pulled 3 laws from that data. Now, what is a law? A law is a mathematical relationship between 2 variables that holds true in the objective reality. In other words, you mathematically describe a prediction of the relationship between 2 things, and then you observe those 2 things, and the observation matches the prediction. That's a law as opposed to a hypothesis where someone just has an idea that's yet to be experimentally tested. So we have 3 laws from Kepler. So Kepler did look at mathematical relationships between aspects of variables concerning the movements, the orbits of the planets around the sun. And he came up with 3 laws, as I said, but he actually came up with the second law first. When he was looking at the movement of the planets through the sky on a nightly basis at the same time of the night throughout the year, he noticed that some nights, some 24-hour periods, I should say, some of the planets, depending where they were in their orbit, were moving further in terms of their apparent movement across the sky, in terms of the angle across the sky they've moved in a day. And at other times of the year, they moved a lower number of angles through the sky. They apparently moved less, from which Kepler was able to make some calculations on the exact ratios of those things. And what he described was that, therefore, the orbits of the planets around the sun were slightly elliptical through to quite elliptical, depending on the amount of variation between the movement on a 24-hour period, and others less elliptical, but ellipses nonetheless. Example, the orbit of the Earth, very nearly circular, very, very slight degree of eccentricity. Other planets more so, but he mapped them all out. And what he found in his second law was that the area of the ellipse that was scribed out in a 24-hour period by the planet concerned on its elliptical orbit remained constant all the time. So when the planet was closer to the sun, it moved more rapidly, hence the area remained constant. And when the planet was further away from the sun, it moved more slowly, and hence it was longer, but thinner, and the area was the same. So that's basically Kepler's second law. The first law was that the planets move in ellipses, as he worked out from the data. Then he came up with his third law, which is really the one which is of most interest here regarding whatever we're going on with Venus up here. Not over there. Venus is there. Not over there. Anyway, fine. I'm working backwards because of the camera thing. So the third law, what Kepler did was he used basic trigonometry in the observations of the positions of the planets in the night sky throughout the year. He calculated the furthest, well, he worked out where the furthest point away from the sun the planet got during the year was, and he then used that to work out that there were exact ratios of distances of the different planets from the sun with respect to the distance that the Earth is from the sun. So we had all the ratios worked out, and we knew basically what all the gearing was. That's basically Kepler's laws. There's a list of the exact number of what's called astronomical units, or AUs, which is the distance between the Earth and the sun, or whatever that is. So Kepler worked out the ratios, but not the distance itself. So all we've got is ratios, so we don't actually know how far away the sun is, or how big it is from any of that, or any of those particular ideas at all. We've just got the ratios. And that's as it remained for quite some time, really, quite a goodly number of years, until another very, very clever chappie came along and was born and trained and learned all sorts of stuff about all sorts of things, really. And then what happened after that was said very, very clever person then suggested, here is a method by which we might be able to closely estimate the actual distance of the Earth to the sun using trigonometry in a very, very clever way. And the way that we're going to use trigonometry is we are going to use a tool which is called Parallax. Now, I realize that a lot of people who subscribe to YouTube influencers like P Brain, for example, about whom I made a very fine video earlier in the week when he was talking about his opinion that crepuscular rays from the sun clearly demonstrate that the sun is very, very close to us and not at all large. I debunked that completely. You'll see that video is available on my fine channel here to go and have a look at. Basically, the people that follow influencers like P Brain are the kind of people who unfortunately do not have an understanding of basic visual perspective concepts. I outline it quite clearly, I think, in my video. So those people are struggling with basic perspective. So those kind of people are likely, unfortunately, to struggle hugely with something slightly more complex, like parallax. So I thought what I'd do to help you out, boys and girls, is put together a little demonstration out the front of my house. So let's go out to the front of my house. Come and join me out the front, and we'll talk about what it is that this parallax thing is and how it actually does work, shall we? Okay, let's go and do that now.
Well, here we are, boys and girls, looking at my Venus from pretty close to it. I'm about 12 inches from my Venus on a pole here. Behind my Venus is my reference. The width of the telephone pole behind Venus, I'm going to say that's the width of the sun nominally. Not to scale, but that's not important. Let's move back and see what I've set up here. Here we have two vantage points, A and B. separated at a distance, as it turns out, just so you know, of 24 inches. Not perfectly vertical, as you can see, not really important here. It's just the concept I want you to understand. What I'm going to do is I'm going to place the center of my field of view directly above position A, and I'm going to find Venus. There it is, on the hard right hand border of the Sun. And now what I'm going to do, let's come back to where I am here. I'm going to move across 24 inches to my other point of reference. There it is. Let's find Venus. Look at that. Now it's actually just slightly out. Oh, here I'm slightly off the. There we go. Now it's in line with the left hand side of my frame of reference. There it is. Once again, left hand vantage point, right hand side of the Sun. Right hand vantage point, left hand side of the Sun. Parallax. Brilliant. Now, why is the scale not so important here? Well, all we really need is some kind of reference, some fixed plane, if you like, behind the article on which we are focusing, which in this case is Venus. I'm now right between the two markers, left and right. There they are. There's my Venus right in the middle of the Sun. If we know how much of the sky in degrees the Sun takes up, that's all we need to know at this point. And we do know that thing. Look at those corpuscular rays. Look at that perspective.
Okay, so here is an image of or a series of images superimposed, really, showing the position of Venus as it transits across the face of the Sun from a given point on the Earth, and it shows the time in British Standard Time at where the planet Venus was, as observed from the Earth. Now, the next image I'm going to show you is this one here, which is kind of a schematic showing you the concept of having two viewpoints that are separated by a given distance, which is 2r, twice the radius of a circle, which is ascribed through those two viewpoints, if you like. And you'll see in the diagram that obviously those lines converge at a given point. And if that point is on an object on which we are focusing, like the pink rubber ball Venus in the outdoor example you've just seen, or indeed this example here of Venus in front of the Sun here, basically, and that will form an angle. Unfortunately, at this point, we don't know what that angle is. And hence we don't know what the height of that triangle actually is, i.e. the distance between the Earth and the Sun. So we're still no further ahead. Until you realize what you did realize, hopefully, when you saw the pink Venus ball moving with respect to the fixed reference point behind it, the post in the ground, the lamp post, the concrete lamp post there. And you'll see that the angle that is coming from the back of Venus going towards the Sun there is the same angle as the angle which defines the height of that triangle as per normal trigonometric calculations. And you'll also realize that viewing the transit of Venus from two different positions on the Earth, separated by a large enough measure of distance, will cause the transit of Venus to appear to occur at a different point across the face of the Sun, which will be separated from each other by the exact same angle. So given that we now have the Sun as a fixed reference point, we can use the angle of difference between the two lines, the two transit lines that we see from different points on the Earth, and thereby determine the exact distance to Venus. As it turns out, we don't get it exactly right. We get a close enough approximation. The reason we don't get it exact is this. There is atmosphere around the Earth that distorts the view of Venus slightly. Very slightly, but enough to sort of throw the calculations off a bit. Secondly, there may well be gas and other forms of matter in the space between us and Venus, thus leading to slight errors. And so that's why it's not an exact methodology, but as it turns out, pretty close, and I'll justify that statement a bit later in this video here. So what you're now seeing is the next image, which is the yellow apparent disk of the globe Sun that we see as we look at it from our vantage point on the Earth. And if we were in the more northern of the vantage points, we would see that Venus transited apparently on the lower of those two lines. And obviously, if we were further south, we would see the more northerly transit line. And so the distance between those lines on a scale model of the Sun, for which we only need the scale of the angle. We don't need the size of the Sun or the distance of the Sun or anything else. We just need how many degrees in the 180 degree of the sky that we can see at any time, how much of that is Sun? Its apparent size, in other words. And then obviously we can work out the proportion of that, which is the difference between those two transit lines, and that gives us the angle. Brilliant. So then we can do the trigonometry and work out pretty much the exact distance to Venus. Isn't it? Very, very good. So in 2012, on the 5th and 6th of July, British Standard Time, a transit of Venus occurred across the face of our Sun, as it does, predictably, and on a schedule which we can obviously predict right down to the very second that we expect it to occur these days. Another indication that the astrophysics and the heliocentric model and Kepler's laws are all working pretty well. I'd really like to see a flat tard explain to me and show me exactly how and predict when we can expect to see eclipses and transits and those kind of things on the basis of their model. I think you'll find they will be struggling mightily. In other words, they can't do it. They have no idea why it happens. Much the same way that they think about this particular little quandary about why it is that apples float on water. So there we go. Anywho, here is a map of the world now that you're looking at, and you can see that the two vantage points that we are talking about for this particular data set are in Honolulu. It's pretty much in the middle of your picture there, and the more northerly one was taken in Anchorage, some amount further north on our very much oblate spheroid Earth. In fact, So from this calculation, we can work out what the distance is between Honolulu and Anchorage. How do we do that? Well, we just do a simple trigonometric chord length calculation on the basis of the number of degrees of separation between Honolulu and Anchorage. And thereby we have the base dimension of the triangle that we'll be using to trigonometrically determine the length of the distance between us and, as it turns out, Venus. We're going to measure the distance to Venus by focusing on that and, getting the reference of the angle from the parallax when the two transit lines differ by a number of arc seconds of view in the night sky. Pretty much. So there we go. That is the theory. Now, let's go and do the actual mathematics so that we can see what it is that comes out of all of that. And then we'll compare it to some other different methodologies of determining the distance between the Earth and the Sun and see what we come up with, shall we? What fun. Let's do that then. Right. The distance to the Sun calculations as worked from the 2012 transit of Venus on the 5th and 6th of June, British Standard Time. Right. What we're actually doing here is not calculating directly the distance of the Earth to the Sun. We are calculating the distance of the Earth from Venus, and from that we can infer the distance to the Sun using Kepler's laws, the ratios between the distances that he was able to absolutely establish so many hundred years ago. So let's do that, shall we? The following was determined using the 5th of June 2012 transit of Venus. It was observed in both Anchorage and Honolulu simultaneously. Very good. So here are some basic information that some of you may or may not already be aware of, but let's just fill it in so people know what I'm talking about here. 1 degree of the night sky, 1 single degree for the night sky is broken down into 3,600 arc seconds. I looked up a distance from an astrophysicist who has published a page outlining these calculations, and that particular bloke said the distance between the two cities was 4,482 kilometers. I double checked because I thought I'm not sure. I'm not sure what that particular bloke did to get that number. However, here's what I did to get my number, which is in brackets, which is actually 4,437 kilometers, straight line between those two cities. I took the chord length calculations for the number of degrees of separation of the two cities, both vertically and, or if you like, latitudinally and also longitudinally around the Earth. I used the different diameters of the Earth, pole to pole, and or latitudinally and longitudinally, if you like. And I did a quick Pythagorean bit of trig there, and I came up with a straight line distance of 4,437 kilometers, a laser beam straight line between those two cities. Okay, let's say that is what it is. If I'm wrong in that calculation, it's a smallish error in terms of the base length, but it does add up, as you'll see in a minute, to quite a big difference in the outcome. Hence why I'm giving you both figures. The apparent angular diameter of Venus, as when it's at its closest point to the Earth, in other words, when it's between the Earth and the Sun at transit time, is 58.3 arc seconds. So that's 58.3 times 1 over 3600th of 1 degree in the sky. So it's like really, really chuffing small in the sky. You need some really, really good magnification to see the thing pretty much at all. That's why we need the telescopes and stuff and some good filters to block out the glare and all that kind of carry on. So that's what it is. The apparent solar angular diameter in the sky is 1891 times 1 over 3,600 arc seconds of degrees. So it's like around about or just over half of 1 degree in the sky as we look at it. So that's good to know for what it's worth. The length of the transit chords from contact 1 to contact 3, which are set points on when the small disk is contacting the large disk in a certain way. It's all mapped out. If you want to go and look at the information on that, look it up for yourselves as to exactly what all that means. You can. Anywho, as viewed from Anchorage, Alaska, the transit of Venus started at 14:06:28 local time and ended at 20:30 and 44 seconds local time on that day, which added up to a transit time of 23,056 seconds for what it's worth. The length from Anchorage, therefore, of the transit in terms of arc seconds. There's the math there: 23,056 seconds times 0.05527 arc seconds per second. In other words, the speed at which it moved gives us 1,274.3 arc seconds from left to right across the disk of the sun, between contact 1 and contact 3 of the transit, as viewed from Anchorage. A lot further south in Honolulu, it started at 12:10 p.m. and 6 seconds and ended at 18:26 p.m. and 37 seconds from contact 1 to contact 3, which works out to 22,591 seconds. The length of that chord across the disk of the sun is therefore worked out as shown there at 1,242.7 arc seconds. Very good. Then those numbers could be applied to a circle of any size to make a scale model of those two arcs, which are parallel to one another but separated slightly on said circle. As it turned out, the separation between those two chords was 14 arc seconds, basically, the transit chord shift, which is like 3.8 thousandths of 1 degree. So not visible with the naked eye whatsoever. You need really good equipment to get anywhere near that. And so that's what was done in 2012 in Anchorage and Honolulu. Now, is that our final answer? Well, no, it still isn't, because I should have said that the circle can be of any size that you do the scale model, because we know how many arc seconds the sun is apparently in the sky on that date. So the proportion of that is the difference between the two chord lines gives us an angle, and the angle is what we need at this point, not the actual distance between them, because we're going to trigonometrically determine the distance from those angles, given that we have the base length, the distance between the two cities. Yeah. Okay, so there we go. From the different viewpoints in Alaska and in Honolulu, the sun is close enough to the Earth that it moves, apparently, by around about 6 arc seconds, which is 6 times 1 divided by 3,600 of 1 degree. So almost none, really. But anyway, you've got to add that 6 arc seconds into the 14 arc seconds of transit shift that was observed to get the true parallax shift of 20 arc seconds, which turns out to be 0.0056 of 1 degree in the sky. So almost none. Because that is such a tiny, tiny shift, that means that Venus is somewhat distant from us, and we can get the exact number using trigonometry now, can't we? So we just go the tangent of the 0.0056 degrees of apparent separation divided by 2, so that we can do the right angle triangle base height hypotenuse calculation there, blah, blah. Anyway, we take the 4,482 kilometers as given to me in the source I looked up for this. We divide that by 2d to get the tangent of 0.0056 divided by 2. And that works out to be about 45 million kilometers. There you go. Math, bitches. Okay, but if you use my calculated 4,437.1395 kilometers, you'll get 45,400,000 kilometers. So very small difference in the base length there, and you get 400,000 kilometers of difference in the calculation from the triangle. Oh well, whatever. Anyway, that corresponds to the Earth-Venus distance in astronomical units of 0.28, because Kepler's laws are just that. They are laws. The ratio of the difference between Venus and Earth and the Sun is 0.28. And so if we use some simple math to work out what 1 AU is, that'll tell us the exact distance as per our observations to the Sun. And it comes out to be, if you believe Mr. Astrophysicist, it's 160 million kilometers, give or take. If you use my numbers, that gives you 162,142,857.14 kilometers. And the reason that we get that is from Kepler's laws. Remember, it's that 0.28 is a fixed, observable, repeatable prediction that bears out every single time an observation is made to such a degree of accuracy that to doubt it whatsoever is fundamentally, utterly ridiculous, even if you are severely flat-tarded. Okay, so if you use Mr. Astrophysicist's numbers, that gives you an error for the actual measured distance to the Sun, which we'll get to in a minute, of 6%, which over nearly 100 million kilometers is not bad, I think, or 8.09524% if you use my numbers. I don't know, whatever. Pretty close, really, given that there is distortion of the atmosphere. There is distortion of any matter between us and Venus that would cause those light beams not to travel in an absolutely straight line, because according to Einstein, that would warp the space itself. It's pretty damn good, actually. And when you're looking at differences between things that are so tiny, I think that's a pretty good effort. So anyway, the actual measured distance to the Sun is 150 million kilometers, not 160 or 162. The 150 million works out to be around about 93 million miles, as claimed by not only me, but anybody else that has ever studied this to any degree at all whatsoever. Pretty much, not 3,000 miles like some of these severely flat-tarded will suggest to you, without any reason or logic behind so doing, actually, except crepuscular rays, they'll say, which, as I say, I dealt with that earlier in the week. So, how on earth did we actually, truly measure the distance to the Sun? Well, still, we didn't. But we can infer it by actually measuring the distance to Venus at its closest point to us, i.e. when it's transiting. How do we do that? Well, we shoot a radar beam at it. Radar is a form of electromagnetic radiation which moves through space at an exact speed. It's just short of 300,000 kilometers per second. The number comes directly out of the Maxwell field equations. It is demanded by those equations. It's a consequence of them. It's an emergent property of the universe. It's a law of the universe. The speed of light is fixed. So we know what speed it is exactly. So what we can do is send a radar beam to Venus, bounce it off Venus, it comes back to us, and we wait and see how long that takes for that to occur, and that gives us the exact distance to Venus, pretty much, which is so close to, as it turns out, 42 million kilometers, as makes no odds, and so therefore the exact distance to the sun is also as close to 150 million kilometers as makes no odds. Don't forget, we worked that out using Kepler's law, 0.28. And 150 million kilometers is both pretty good agreement to either 160 or 162 using the accuracy of the transit method. So it corroborates, it's a cross-check, it agrees pretty well. Whether it's 150 or 160 or 162, they're all fairly close relative to each other in terms of value. 3,000 miles, no, nowhere near, not even remotely close. Absolutely, utterly ridiculous, you flat-tarded individuals. And also for your interest, the same method was used to calculate the distance to the asteroid Eros recently. So there you have it, pretty much in a nutshell. That is how we know the distance exactly to the sun from the Earth. So that brings us to the summary, pretty much. There you go. That's what it is. That's what they've done. They've used the laws of parallax to work out the angle of apparent shift in the transit lines of Venus across the sun, a known fixed reference background. That's given us some trigonometric, very close estimations of the exact distance to Venus. That agrees pretty much with the electromagnetic radar method pretty well. There you go, sorted. That's how we know. Hope this has been helpful. Hope you've learned something. Please though, the Flat Tailor, do absolutely come on my channel and tell me I don't know what I'm talking about and it's all nonsense and what is this, etc., because we do need a good laugh here, don't we? Those of us who actually understand that triangles are a real thing, and it's pretty straightforward, really. There you go. That's astrophysics news today, I guess. Although it's not really news today, it's pretty old news actually, but there you go. It's settled. I was asked to put this video together. Somebody, in the usual flat-tarded manner did want to say to me, "Oh, how do you know it's that far to the sun? How can you prove that?" Well, there you go. There it is. Hi, Venus. Nice to see you. Good to see you, boys and girls. Tune in later in the week when I'll be talking about other things actually related to my usual topic matter, which is more about human nutrition and less about the shape of the world. There you go. See you then. Ciao.